Hello everybody, this is Math 1151, and today we're going to do 5.1 and 5.2 from your, no wait, we're not going to do that. This week we're going to do 5.1 and 5.2 from your textbook. That's all we're going to do this week. And it's going to be some smorgasbord of combination of those two things the entire time. Does that make, that probably doesn't make any sense, but, so what's the topic? Well, so far we've been talking about derivatives. We've been talking about derivatives almost the entire time. In the beginning we talked about functions for like a day and then limits for a little while, but we're really moving towards derivatives the entire time. Now we're going to change gears, sort of, and we're going to talk about something called integrals. Integrals. I'll write that down, integrals. Okay, so, and again, I don't think I'm going to directly do 5.1. Like, I'll be like, here's 5.1, 5.1, 5.1. Now we're doing 5.2. I'm going to kind of talk about it all at once, if that's all right with anybody. It's all right with me, and that's what matters. Integrals, what the heck are they? What are they? Integrals compute signed area. Integrals compute signed area. So here's the deal. If I have some picture, I want to give you the picture idea. So everything in calculus is very physical. Everything has a physical meaning. It's not just symbol pushing. It's not just sort of manipulation of symbols. There's some meaning behind almost everything. And so if I have a point here, I'm very comfortable with letters, but how about I put numbers there instead, okay? It doesn't matter. So I'll put, this looks like it could be 1, and this looks like it could be 7. And if I have some curve, it looks like this. This is f of x. I just made that up. So we have a bit of notation. Oh, and I've used it before. It's the same, terribly, horribly, unfortunately, it's really too bad that the notation for integrals is very deadly similar to the notation for antiderivatives, right? And those who have had calculus before will be like, yeah, I know. Okay? And they'll be like, and I know why, too. But I'm not going to tell you why. I'm going to pretend like I don't know why. So remember, this is the notation for an antiderivative. Do you guys remember this from last time? I was even hot pink last time. And typically what you do is you put some function in here, f of x, and then you put the variable here, dx. And the only difference between this and the notation for an integral is, I got to get the right color. I hope nobody's colorblind here. Is you have, for this example, I'll put in 1 and 7. And as soon as I put those numbers in there, it means something totally different. This equals a number. This equals a number when I do that. And compare that, and this is a definite, this is what's called a definite. And if you don't always have to say this. This is an integral. And what's it? Integrals on what type of thing is it at the end of the day? It's a number. It's a number. When you want to understand mathematics, the most basic way to understand something is to understand what the type is of the answer. Is the answer a function? Is the answer a number? Here, the answer is a number. Compare that to an antiderivative. An antiderivative, also called an indefinite, and I'm writing this small so nobody can read it online. an indefinite integral. And the notation is very similar. The notation is very similar. It looks like this. You have the d here, and you have f of x, and you have an x here probably. But it equals a function. That's good. So whoever said it's a function. A function. And it doesn't actually just equal one function. It actually is a whole bunch of them, right? It's like you write plus c, right? That's to represent all possible, like many. Yeah, sure. Many, actually. That's bizarre and it can break your mind trying to think about all the functions. And what's the only difference between these things? Well, this one, watch this here. Pedagogy right here. Pedagogical Innovations by Dr. Snapp. You ready? Watch this. What's the difference? There's nothing. There's nothing there. See, I made it less. And here you have numbers. These are, the bad thing is that this notation is so similar, but they mean very different things. This equals a function, actually many. This equals a number. Now here I say, integrals compute signed area. If I ever ask you what's an integral, you say, it's something that computes signed area, Bart. And then I say, what's that mean? You're like, I don't know. Well, here, let's see if we can explain that. This is the integral from 1 to 7. And so we have a function. This is our function right here. And here's 1. And here's 7. And integrals compute signed area. And so blue is I was about to say blue is a happy color, you know, blue skies. But maybe blue is a sad color. Okay, so blue is a sad color, obviously. And so here is the area. It's the signed area between our function and the horizontal axis. So this is the blue area, and then we need a happy color like sunshine, maybe. Okay, here we go. And this is the area. There's the happy area, right? And so the integral, what it does is it computes, this is the plus area, the sign, the positive area. And you might say, how can you have negative area? I don't know, you just do, okay? Here you have the minus area. And what it does is it computes this thing, and then it subtracts the minus area. They cancel each other out, obviously. I said obviously because maybe it's not so obvious. That was a joke. So these kind of cancel each other out, and then you get a number at the end of the day. All right, so let's, and so you should think of this integral. It's a machine that computes the area. How does it compute the area? I don't know. It just does. All right? It just does. And so you might say, well, that seems pretty useless. Well, maybe, I don't know. Let's see if we can compute a couple integrals on our own, only knowing, being, you know, I'm a naive person, you know, and all I know is that integrals compute signed area. How do they do that, Bart? I don't know. But I know they do it. So can I do any calculations? Of course I can. Check this out. Let's do an easy one. Here we go. Here's my axes. I'm labeling it for some reason. I'm not sure if that's even right anymore. And I take my favorite curve, x cubed. Hopefully you're asked that on an exam someday. What's Bart's favorite curve? It probably never will be. But it's x cubed. So here we go. I'm plotting x cubed. There it is. There is x cubed, right? And suppose I want to compute the integral. Now, an integral computes signed area, right? Computes signed area. Suppose I want to compute the integral from, I don't know, -2 to 2 of x cubed dx. This computes the signed area between x cubed in the x-axis. Now, I'm going to try to be consistent. Blue is positive, and no, blue is negative, and orange is positive, obviously, right? So I need some limits of integration here. I forgot the chalk. There it is. Okay, I'm going from -2 to 2. Okay, great. This is 2. This is -2. What is x cubed of 2? 8, right? So it goes up here to 8, and here we go, and this goes down here. And put this right there. And aha, there's my negative area. Do you guys agree? It's the area between the curve and the x-axis, and it's below the x-axis, so it's negative. And there's the positive area, right? There's the positive area. You guys good with that? Oh, what's the integral going to be? 0. The areas are exactly equal. So this one's equal to 0. So knowing nothing but integrals compute signed area, we could do that one. All right, we can do another one. Here, this next one I like. And of course forget it. Anyway, so the next one is this. Here we go. It's got to find the eraser. Eraser 0, 3. We're hid eraser. Here we go. Okay, so sorry. He says, what would the integral for the first one be? I don't know. Can you tell me anything about the number? Can you tell me? It's a number, right? Can you tell me anything about it? It's got to be positive. It's a positive number. Because this negative area is less than that positive area. That's all I can tell you at this point. All right? So he says the number on top, that's the number on top is the thing you're going to. It's like you start here, and then you go there. And you might say, why can't you just say it the way I said it, Bart? Because if I switch them, it negates everything. But we'll get to that. All right, we'll get to that eventually. All right, so I want to compute signed area, and I have this new machine, and I want to try it out. So here it comes. Let's see. Here's my axes. I'm labeling x and y for some mysterious reason. Okay, so here's a function. It's here's a curve. Y equals x. Y equals x. It's a line. And let's call it f of x equals x. I'm sorry. No, that's fine. Y. I'm sorry. Sorry. Okay, so now the integral from 0 to 3 of x dx, that's going to compute the signed area from 0 to 3. There we go. What type of shape is this thing right here? It's a triangle. This is a triangle. And what color is blue? It's blue. It's negative, right? Sunny. Sunny, sunny. Okay, there we go. Okay, and so what's the formula for the area of a triangle? 1/2 base times height. So this thing here, and the height is 3. So the area is 1/2 times 3 squared. Right? So the integral is equal to 1/2 times 3 squared. Definite integrals compute signed area. And definite integrals have the numbers here. Indefinite integrals are antiderivatives, and they don't have the numbers there. All right, let's do another simple example. I have all week. Okay, what's the next example, Bart? What's the next? I'm going to just copy. I like this one. This one's good. Okay, so here, the integral from -1. By the way, if you have your hand up, just shout it out. Okay? Yeah, what's up? No, you shouldn't simplify that answer at all. No. Any other questions? You just shout it out. Say, hey, Bart, pay attention to us. Okay. Maybe I should draw the picture first. Here's what I want to integrate. I want to integrate from x to y. I want to integrate f of x equals the floor of x. You guys remember the floor function? The floor function takes the greatest integer less than or equal to the number. Okay, so the floor of 4.3 is 4. The floor of 5.7 is 5. The floor of 6 is 6. What's the floor of negative 2.1? Negative 1. It's the greatest. Well, wait. Negative 2. Negative 2. Thank you. I don't know. That was a hard question. That's why I asked you. Okay. So here's our floor function. So negative 1, it looks like this. It goes from here to here. And then it's open. And then at 0, it's 0 all the way to 1. And then at 1, it's 1 all the way to 2. And then whoop. And then to here. And then, oh, right there. There we go. And maybe I should label some things here. So this is 1. There's 2. There's 3. And here's negative 1. I'll put it in the same. All right. So we want to compute, I want to compute the integral from negative 1 to 3 of the floor of x dx. And integrals compute, they compute signed area, right? They compute signed area. And blue is my negative area. And so there's some negative area, negative 1. And then it's all positive area after this. There's positive area. And here's positive area. And I'm going all the way to 3, but this is just a dot. No area under a dot. Right? Because area of a rectangle is length times width. And what's the width of a dot? 0. It has no width. So there is the thing I'm computing the area of, right? All right, well, can anybody just tell me the answer? It's going to be, isn't it going to be 2? And the way I did it was I said, well, this here cancels with this here. And then it's just a 1 by 2 rectangle. Does anybody agree with that? Yeah, so that's easy. That's easy. Equals 2. Equals 2. Why would the 1 from 0 to, why would this have 0 height? Okay, so it's the floor, right? And so let's think about numbers between, so the floor of 0 is 0. The floor of 0.1 is 0, because it takes it just throws away the decimals. And the floor of 0.5 is 0. The floor of 0.6 is 0. Floor of 0.7, 0.8, 0.9 is all 0. But the floor of 1 is, so then it shoots up. Did I answer your question? Awesome. Okay. All right. So now, just remembering that integrals compute signed area, just remembering the integrals compute signed area. There are some properties of integrals that we can write down really quickly, and we can say, oh yeah, that's obvious. That makes perfect sense. Okay? And so the first thing we can write down is that the integral from a to b of some constant, the integral from a to b of some constant is dx is equal to kb minus ka. What? Why is that true? Here, let's see if we can explain this really quickly. This makes perfect sense. It really does. You should just be like, yep, I know that. Here we go. X, Y, gotta find some more chalk. A constant has constant height, right? Here it is. Whoop, like this. And then if I have A and B, so what am I doing? I'm computing area from, when I multiply K, that's the height, by B, that's the area of this whole rectangle, and then I'm just subtracting off the area of that rectangle. So this is why this makes perfect sense. There's no, from the idea that it just computes area. Great. That's all this does. It's very simple. It's computing area. Okay, so now here's the next one. This one's a little harder, I think. I don't know. Integral from a to b of f of x plus g of x dx is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. This one is harder. This is more difficult. But the idea is, you know, if you have a function this high, you compute its area, and then if you added some function, it just makes it that much higher, giving you that much more area. I'm not going to say any more about this. And then here's another fact. The integral from a to b of k f of x dx is equal, you can factor out the k, b f of x dx. Okay, great. And here's some, I'm going to give you one more, even simpler fact, which probably I should have given first, but I forgot that these were harder until I wrote them down. So here's the even simpler fact. If A is less than B is less than C, then the integral from A to C of f of x dx is equal to the integral from A to B of f of x dx plus the integral from B to C of f of x dx. Now look, this really makes perfect sense. This is very sensible. If you have A, B, and C, I have some curve here. And so we're saying that the integral of the whole space from A to C is equal to this area plus this area. Makes perfect sense. If you just remember what the integral sign means, it computes signed area, you're good. What questions do you have? All right. I'm going to ask you a couple questions here and see if you can answer them. Here we go. Here's some questions. This question's not too bad. It's a nice medium question. Here we go. Suppose you know, there's something you know, I'm just telling you right now. The integral from -1 to 1 of x squared dx is equal to 2/3. And you also know that the integral from negative 1 to 1 of e to the x dx is equal to e minus 1 over e. You know that. So my question is, what is the integral from minus 1 to 1 of 4 e to the x minus 3x squared dx? What is this? You know the other stuff. How do you compute this? And your answer should mention these things. I'm going to let you think about this for just a second. How you do it. I'll do some housekeeping. So what do you do? How do you solve this? We want to use one of these, right? Is that what you're saying? A multiple, right? Well, first, I would break up the sum. Okay, this minus, right? This is equal to the integral from minus 1 to 1 of 4 e to the x dx minus the integral, I could do plus, whatever, minus 1 to 1, 3x squared dx, right? And now I can pull out those multiples. I can pull out that 4. I can pull out that 3. We'll do that. I know I'm erasing the properties. I'm sorry. Not that sorry. If I was really sorry, I probably wouldn't be doing it. But that's okay. Okay, so now this is 4. This is equal to 4 minus 1 to 1 of e to the x dx minus 3 integral minus 1 to 1 of x squared dx, right? And now I just substitute. So this is equal to 4 times e minus 1 over e minus 3 times 2/3. Good? What? Stop it right there. So this is all good and well. What questions do you have before we move on? Yeah, what's up? Why aren't the integral symbols here? Here, let me just put this e a little higher. There we go. It's because I know that this whole integral here, this thing here, which is the same as this one right there, is equal to 2/3. So this whole piece, this whole thing right here, got replaced by the 2/3. And this whole piece, remember, this computes a number, right? Got replaced by the e minus 1 over e. Did I answer your question? Okay, what's up? Where did the 3 come from? So the first step we did was we took kind of this piece here. Oh yeah, here's a 3x squared. No, it's okay. And then this 3 here came out because I'm allowed to pull out constant multiples. All it does is shift the area before or after. What's up? An oracle told me. Yeah. How do I know? That's how. But it's a good question, you know. How do we know the area? When the line is a diagonal line, it's a triangle. And we could use some facts that we know about triangles to help us out, right? But even better than triangles are rectangles, because rectangles, the formula for the area is this base times height, right? And so, really, how are we going to find, like he says, x squared? How the heck can we compute this area here? And just to give you, I mean, when I'm doing integrals, to be honest with you, I'm not even kidding, I'm drawing pictures all the time. I'm trying to say, what am I doing? What's going on here? To make sure that I'm doing it right. And so let's focus for a second on this problem right here. So I have this, I have x, and I have y. And then so there's my curve, right? And I'm going from -1 to 1. And, oh, is this area positive or negative? It's positive because it's above the x-axis. The only thing that matters is that it's above the x-axis. And so there's the area we're trying to compute. But that doesn't have a nice shape that we know the formula for before the fact. So if we could only find some way of computing this formula, that would be a lot easier. Here's an idea. Here's an idea. What we could do, if we wanted to find this area, suppose we wanted to approximate this area, what we could do is I'm going to zoom in. Here I am. This is supposed to be, I'm just zooming in on this side, okay, to 1. What we could do is we could well, there's lots of ways we could do it. I want you guys to think, okay, so here's the question. Imagine, I'm going to paint a picture for you. All of a sudden, you feel an intense urge to stand up and leave the class right now. And you decide not to come back, do any homework, or look at the textbook until the exam. Okay? That'd be a bad idea, right? I think it would be a bad idea. Maybe you think it would be a good idea. Now, here's my curve. And on the exam, we ask you to compute the area between -1 and 1 of x squared. And pretend you've never had calculus before. You have no idea how to do this. But you do remember one thing. You remember that integrals compute signed area, right? How could you try to, you write a little note to your TA, say, well, shoot, I didn't come to class. But here's my best shot. Take it or leave it. That's what you write. We like stuff like that. I like stuff like that. I don't know if anybody else does. So how could you try to compute this area here? What could you do? You could start with a triangle. She says, hey, you could approximate this. This kind of looks like a triangle, right? She says you could approximate it to a triangle, and then maybe you could make 2 more triangles, and then subtract it off, and then you maybe kind of get close. That would be a good idea. What else? Any other ideas what you could do? Yeah? What you do is you sample the curve. You sample the curve. Okay? I'm just repeating what this guy said. You sample the curve. Here you go. There's the sampling. And then you make a bunch of rectangles is what you do. You make some rectangles. Now, this is child-safe chalk to make sure that children don't eat the chalk because it looks so delicious. Ah, yummy. Okay, so he says you sample it, and then you make some rectangles of the appropriate height. There's some rectangles, and we can compute those rectangles. Can anybody think of a different way of computing the Use the tangent lines. We know derivatives, right? Use the tangent lines. It's kind of like her idea. Use triangles, right? Does anybody think of any other way, something even totally different than what we talked about? Yeah? I haven't talked about it in class at all. So what I'm thinking of, I have not talked about. Newton's method or Riemann sums. Well, we'll be talking about Riemann sums soon. Anything else that doesn't even seem Any other ideas? So if you're a physicist or an engineer and you have a difficult integral that you want to compute, a standard way to do it is what you do is you make a little box around the whole thing, and you just fill it with random points. You just fill it with random points. Put random points down, and then you ask yourself, is the random point above the curve or below the curve, right? And then you count how many are below the curve, and you count how many are above the curve. Does that kind of make sense? Probably seems really simplistic, like, wow, what a stupid method, okay? You know what's great about it? It usually works. It's called Monte Carlo integration. Just put a bunch of points down and hope that you put down random points, and then you count, okay? So that's one way. We're not going to do, the way that we're going to use, of course, is we're going to use this rectangle method. We're going to use a bunch of rectangles and add them together. Now, I can still remember my Calc 1 class, and I remember I was terrified of a lot of things, but one thing I was especially terrified of was the following. I'm going to show you right now. I was afraid, and basically I was sure that if my teacher started doing what I'm about to do, I would not learn it. Okay? So I was pretty confident of that. So let me show you, and let's see if I can convince you that you can learn it. You guys have seen this before? Right? Is this thing kind of scary? Oh, good. I'm glad. You know, that guy says yes. Honesty. That's great. This thing's kind of scary. Okay, so let's talk about this for a second. See if we can make this work, and then we'll see if we can then talk about this. Okay, so this is a sigma. It's a Greek S, right? Greek S, sigma. It's a big sigma. Okay, and it stands for sum. Sum like add, repeated addition, right? And it has some decorations on it. Okay, and so here we have the sum, and what we're going to have is we'll have a variable here. So k, all right, k equals 1 here. There's our k equals 1. And usually you have some variable here. Now I'm just going to put k right there. That's what I'll do. And then you have something on the top. And I'll put 8. I'll put an 8 here. And so today, what I'm going to talk about right now is just what this contraption means. And then we'll talk about how to do it. That's all I want to talk about. What does this crazy contraption mean? So the way you think about this is you think about it as like a loop in like a computer language. It really is a loop. So this is equal to, and what's k right now? K is 1. So it says, write down k. Go to the next number. 1. Now k is 2. Write down k. Go to this doesn't really say go to the next. If you're less than or equal to 8, go to the next number. Plus 2. Down, now k, here, I should even do this. Maybe, okay, yeah, I just had a good idea. I just need all that needs to happen is the purple chalk needs to find its way into my hand. So it's like 2, there. And then 3 goes to here. And then you have 4. And that goes to plus 4. And then you have 5. And that goes to, if you guys see, plus 5. And then 6. And that goes to plus 6. And 7. That goes to plus 7. And then 8 goes to plus 8. And now we're at the 8, right? So we stop. What's up? Does it have to be an integer? So what do you mean does it have to be an integer? He says, what about 1.1? Typically it is an integer, okay? If it's not an integer, then you have to put some other information in there. I think for you it's always going to be an integer. So that's pretty easy, right? Is that okay? Let's do another example. Is that all right? Let's do another example. And the way to really make this, I like this exercise. It's kind of a silly one in some sense. Just write out what the sum means. What? Oh, does this tell us? Well, that thing doesn't directly tell you, right? We're going to use that to tell us. Because what we're going to do is we're going to write a formula for the area of each rectangle, right? And then we're going to have a certain number of rectangles. And then we're going to want to add them together. So it's going to be the sum of the formula from 0 or 1 to the total number of rectangles, or the total number of rectangles minus 1. We start counting with 0. 0, 1. How many fingers am I showing you? Yeah, 0, 1, right? So. Oh, okay. So here, we need to know some formulas. So let's write down some formulas, and I don't want to mess them up. I want to get them right for you. Okay, and so let me just make sure that I don't screw this up, because can't tell, but maybe you can. I'm nervous. Yeah. Okay, so here we go. The sum of k equals 1 of k. And if we go all the way to n now, before we went to 8, now we're going to n. So this thing's equal to 1 plus 2 plus 3 plus 4 plus dot, 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 plus n minus 1 plus n. We go all the way to n. N's some fixed number. It's like 16. We just add 1 plus 2 plus 3 plus 4 plus 5 all the way to plus 16, whatever. This is equal to, this is a formula, okay? N times n plus 1 over 2. Now, suppose you don't believe me. Suppose you don't believe me that this is true. First of all, I could prove this to you, but we're not going to do that, okay? Because I think that would just, I don't think most people need it. I think a more convincing argument would be, let's try it out. Let's try it out and see what happens. So if I want to sum to, what if I sum from, and I'm going to try it out playing with the summation notation. That's what I'm going to do. Just to remind you. So if I want to write out the sum from 1 to 3, 1 plus 2 plus 3, what do? I write the sum, right? And then I'm using k, so k from 1 to 3, and I'm just summing that number. And so this is equal to 1 plus 2 plus 3. What's 1 plus 2 plus 3 equal to? 6. This is equal to 6. Now I say it's also equal to that formula right there, right? I say it's equal to that formula. Let's see. What's n equal to here? N is, yeah, perfect. N is equal to 3, so it's 3 times 3 plus 1 over 2. That's 3 times 4 over 2. That's equal to 6. It looks good. What do you guys think? Is it okay? Why? He says, why? Why is that true? Yeah. Show of hands. How many people want to see why it's true? How many people don't want to see why it's true? Okay, the don'ts have it. If the do's want to see it, I'll show it to you later. No problem. I can show it to you after class. It's not going to take that long. That's okay. I respect the will of the people. No, I don't. Anyways, okay. So this is a good formula to know. Okay. So there's one formula that you should know. Let's do another one. Here it is. This is the one I always forget. I'm going to forget this one, right? I've forgotten it already. It's gone. It's not in my head. I'm going to look it up right now. I'm going to cheat. What is it? It's, yeah, n times n plus 1, 2n plus 1 over 6. I'll forget it by the time I write this out. All right, it's the sum from 1 to n as k goes from 1 to n of k squared. So what's this thing equal to? Let's see. It's equal to, if k equals 1, it's 1. Plus, when k equals 2, 4. Awesome. When k equals 3, 9. Plus 16 plus dot, 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 plus n squared. Does that kind of make sense? You go through, right? You should practice like writing one of these things out. It'll help. This thing's equal to n times n plus 1 times 2n plus 1 over 6. Well, at least I say it is. How should we check? Let's check it with at least one example. Okay, let's check with at least one example. I don't think going to 3 is so bad, so we're going to do the sum from 1 to 3 of k squared, right? So the sum, k equals 1 to 3 of k squared is equal to 1 plus 4 plus 9. 1 plus 4 plus 9 is equal to 14? Yeah, it's equal to 14. Aha. So now we plug, we're going to 3. Let's see if this formula works. I hope it does. If it doesn't, then I'm an idiot. Okay? Well, I might be an idiot anyways, but we'll see. Okay, so it's 3. What's 3 plus 1? Times 4. What's 2 times 3 plus 1? 7. Oh my God. Divided by 6. It's amazing. It's a miracle. It works. 14. There we go. We can explain this one very easily too, actually. But if anybody wants to stay after, I'll show you how to do it. So that's our second formula, and here's our third big sum formula. You guys haven't asked me the question that I'm dreading that you asked me, so I'm going to tell you to ask me the question that I don't want you to ask me. You should say, don't we have to know this? You know, and the answer is, I don't know. You guys should send me an email and say, Bart, figure out if we need to know this or not. That's what you should do. Somebody send me an email. Bart, do we need to know all those formulas, or will they be given to me on the exam? Because that's a good thing that you should know. Don't you think so? Yeah. So send me an email, because you know what's going to happen? I'll leave the class, and then I'll forget that I was ever here. Why do you think I videotape it? It's like a bad movie from the 90s, or a good movie from the 90s. Okay, so. All right, so the next one. Here's the next formula that we're going to be using some. And why am I writing all these down? It's because I want you to get this a feel for the summation notation. That's really what I'm trying to do. Also, these formulas are good, and also we're going to use them here. But I want you to just sort of get the feel. So I'm going to sum the cubes now. I'm going to sum the cubes. So here's my sum. It's the sum. When I write this down, I'm like, it's the sum. I'm moving my mouth. It's like when I read, you know. The sum as k goes from 1 to n of k cubed, that's equal to 1 plus 8 plus 27. You could just write the number cubed if you wanted to, but I wanted to show off that I knew that 3 times 3 times 3 equals 27 plus n cubed, right? And then this is equal to n squared times n plus 1 squared over 4. This is equal to n squared times n plus 1 squared all over 4. All right, let's see if it works. We'll do our standard sum from 1 to 3. Right? We'll do our standard sum from 1 to 3. I should have done these in different colors. This is not going to be exciting. Okay, so here we go. Oh. Standard example, here we go. So I have the sum, here it is, that's the sum. I'm saying it as I write it, from k equals 1 to 3 equals 1 plus 8 plus 27. 1 plus 8 is 9 plus 7 is 16, so this is equal to 36. Equals 36. Okay, and then I say this is equal to n squared times n plus 1 squared over 4. What's n equal to? N's equal to 3. So 3 squared times 3 plus 1 squared over 4 is equal to 9 times 16 over 4. But look, the 4's cancel, and I get 36. It's looking good. All right, we'll start here next time. Have a nice day, everybody.